Hello there, and welcome to the Astro Sleep channel. I am so glad that you found your way here tonight. Whether you are curled up in the safety of your bed, listening under the weight of a heavy blanket, or perhaps gazing up at a ceiling where shadows play like slow tides, I hope you are comfortable. I hope you feel safe. The day is over now, and whatever tasks or worries may have followed you this far, you can gently set them down outside the door of this quiet space we share. There is nothing left for you to solve tonight. There is nothing left for you to organize or answer. You have arrived at the time for rest, a sanctuary where the only requirement is that you breathe and let the world drift away. Tonight, we are going to embark on a journey that is both very old and strangely new. We are not just gazing at the stars above us, nor are we wandering through ancient forests of moss and stone. Instead, we are going to turn our gaze inward, drifting deeper and deeper into the very fabric of the reality that holds you. We are going to explore the world of quantum physics. Now, I know that for many, those words might summon images of chalkboard equations, frantic calculations, or the sharp, bright lights of a laboratory. But tonight, we are not here for the math. We are not here to memorize formulas or to strain our minds against the edges of logic. We are here for the poetry of it. We are here to float through the strange, shimmering mist that lies beneath the solid world we think we know. We are going to visit a realm where the rules of the everyday do not apply. A place where particles can be in two places at once, where matter is not solid but a vibration, and where the universe itself seems to wait for us to look before it decides to be real. It is a world that feels less like a machine and more like a dream, a landscape of infinite possibilities waiting to be chosen. It is the perfect place to lose yourself, to let your mind wander through the soft, hazy borders of existence until you find sleep waiting for you on the other side. If these calm, curious explorations help you unwind, I invite you to like or subscribe. It helps other sleepy souls find their way here too. And now, there is nothing left for you to do but rest. Let us take a moment to settle into this stillness. I want you to turn your attention to your body, heavy and warm in your bed. Feel the support of the mattress beneath you, holding you up so that you do not have to hold yourself. Let your shoulders drop away from your ears, releasing the tension of the day. Unclench your jaw and let your tongue rest loosely in your mouth. Feel the slow, rhythmic rise and fall of your chest, a gentle tide that moves in and out, independent of your effort. Imagine for a moment that the gravity holding you to the earth is softening. It is no longer a heavy anchor, but a gentle embrace, a warm hand steadying you as you begin to float. The solid walls of your room are fading into the periphery, becoming soft and translucent. The noises of the outside world, the distant traffic, the wind, the hum of appliances, are drifting further and further away until they are nothing more than a quiet white noise, a background hum that wraps around you like a cocoon. We are going to shrink down now. In your mind's eye, imagine we are drifting past the world of large things. We are floating past the chairs and the tables, past the walls and the windows. We are moving smaller, passing through the fibers of the wood, passing through the lattice of the air molecules themselves. As we go deeper, the world becomes spacious. The clutter of objects disappears, replaced by vast open spaces filled with a quiet, vibrating energy. We are entering the quantum realm. It is not dark here, nor is it blindingly bright. It is filled with a soft phosphorescent glow, like moonlight filtering through deep water. Here, in this microscopic cathedral, there are no hard edges. There are no sharp lines dividing this from that. Everything is fluid. Everything is connected. The particles that make up your body, the atoms that make up the air you breathe, the energy that flows through the stars. Here, they are all just ripples in a great, silent ocean. You are safe here. In this place of fundamental uncertainty, there is a profound kind of peace. Because if nothing is fixed, then nothing is heavy. If reality is just a cloud of possibilities, then you are free to simply float among them, weightless and unburdened. We will drift through this landscape together, moving slowly from one wonder to the next, watching the universe dance its slow, mysterious dance. So, close your eyes if you haven't already. Let your breathing slow down even more, matching the deep, ancient rhythm of the cosmos. Let your mind become as light as a photon, as fluid as a wave. We are ready to begin. We are ready to step into the mist. We begin our journey by drifting back in time, back to a moment when the world felt almost entirely understood. At the turn of the 20th century, the great library of physics seemed to be nearing its completion. The laws of motion, drafted by Newton, were solid and unshakable, governing everything from the falling apple to the orbiting moon with a clockwork precision that felt eternal. Thermodynamics was tidy, explaining how heat flowed like a fluid from warm to cold, and light was nicely tucked into the elegant framework of electromagnetic theory, behaving as a smooth, continuous wave. It was a golden age of certainty, a time when some scientists believed that all the great questions of the cosmos had already been answered, and that the universe was a machine whose gears we had finally mastered. There were only a few odd bits remaining to be cleaned up, small discrepancies that looked like mere dust in the corners of a well-swept room. But in those quiet corners, a revolution was waiting, sleeping in the glow of a heated object. There is a simple mystery in the way things glow. When you warm a piece of metal or a lump of coal, it begins to change. It does not just get hot, it begins to speak in the language of light. First, it glows a dull, deep red, like the embers of a dying fire. Then, as the temperature rises, it shifts to a bright orange, and finally, it blazes into a brilliant white. This phenomenon, known as black body radiation, is something we have all seen, something so ordinary it feels like it requires no explanation. And yet, when the physicists of that golden age tried to describe this glow using their perfect, continuous mathematics, the universe refused to cooperate. The classical equations, the ones that had held the world together for centuries, predicted something bizarre and impossible. They suggested that as an object got hotter, it should emit infinite amounts of energy at shorter wavelengths, spiraling upward into the ultraviolet range without limit. This was not just a small error. It was a mathematical disaster, a scenario so ridiculous that it was given a name that sounds almost mythic: the ultraviolet catastrophe. It was as if the laws of physics were predicting that a simple toaster should unleash enough energy to dissolve the room, a clear sign that our understanding of reality was missing a fundamental piece. No amount of tweaking the old equations could stop the math from spiraling into nonsense. The smooth, continuous world of classical physics had hit a wall. And so, we meet a quiet figure in this unfolding story. A German theoretical physicist named Max Planck. In 1899, Planck was not looking to overthrow the laws of nature. He was a man of careful thought, a pragmatist who firmly believed in the classical worldview. He simply wanted the math to work. He wanted to fix the equation so that it matched the gentle, finite glow of the real world. And to do this, he did something quietly revolutionary, something that would change our perception of reality forever. Planck introduced a small, strange idea into his calculations. he asked a question that had never been asked before. What if energy could not be emitted in just any amount? What if, instead of flowing like a smooth, unbroken stream, energy came in tiny, indivisible packets? Imagine a stream of water turning into a cascade of individual droplets, or a smooth ramp suddenly revealing itself to be a staircase. Planck suggested that energy behaved like coins that you cannot split in half. You can have one packet, or two, or three, but never 1.5. He called these tiny, discrete packets quanta. This was a dramatic shift from the continuous view of the world. It suggested that at the smallest level, the universe is not smooth. It is granular. It is made of steps. Planck found that the size of these energy packets depended on the frequency of the radiation, a relationship governed by a number now known as Planck's constant. It was a number imaginably small, a tiny whisper of a value. But when he plugged this concept into his equations, the infinite energy problem simply vanished. The math calmed down. The predictions matched the warm, steady glow of the real world. Planck had solved the catastrophe. And yet, in the quiet of his study, Planck did not quite believe what he had found. He described his own solution as a mathematical trick, a clever sleight of hand to make the numbers behave, rather than a description of how the universe actually worked. He assumed that eventually someone would find a better explanation that would return the world to its smooth, continuous comfort. He viewed quantization as a temporary patch, a bandage on a theory, not realizing that he had just laid the cornerstone of an entirely new reality. He had lit the first match in a slow-burning fire that would eventually consume the old world and reveal the quantum realm beneath. As we drift further into the 20th century, we find that light itself began to unravel the old certainties. For a long time, thanks to the elegant equations of James Clerk Maxwell, light was understood to be a wave, a beautiful ripple traveling through the electromagnetic field. It bent around corners, it diffracted, and it interfered with itself, behaving exactly as a wave should. But there was another dusty corner of physics, another riddle involving metal and light that refused to fit this picture. It was called the photoelectric effect. The setup was simple. If you shine a light on a metal surface, the energy from the light can kick electrons loose, ejecting them from the metal. In the classical view of light as a wave, the brightness of the light should be what matters. A brighter light is a bigger wave, carrying more energy, and therefore it should shake the electrons loose more violently. It feels intuitive, like a larger ocean wave moving a heavier stone. But when scientists looked closer, the universe surprised them again. They found that the brightness of the light did not determine whether an electron was kicked free. You could shine a dazzlingly bright red light on the metal, and nothing would happen. The electrons would stay put, undisturbed. But if you used a dim blue light, a light with a higher frequency, the electrons would pop off instantly. There was a threshold, a specific frequency required to unlock the electrons, and below that frequency, the light was powerless, no matter how intense it was. The wave theory could not explain this. It was a lock that the old keys could not open. Into this mystery stepped Albert Einstein. In 1905, a year that would be remembered as a miracle for science, he published a paper that changed everything. Building on Planck's hesitant discovery, Einstein proposed something bold and absolute. He suggested that Planck's energy packets were not just a mathematical trick. He proposed that light itself is grainy. He suggested that light is made of individual particles, tiny bundles of energy traveling through space, which he called quanta of light, and later, photons. In this new vision, a beam of light is not a continuous wash of energy. it is a stream of tiny bullets. Each photon carries a specific amount of energy determined by its frequency, its color. A blue photon carries more energy than a red photon, and the interaction with the electrons in the metal is one-on-one. A single photon hits a single electron. If that photon has enough energy, if it is blue enough, it can knock the electron loose. If it does not, it simply bounces off. And no amount of low-energy photons can do the job. Together, it is like trying to open a heavy door. 1,000 gentle taps will not budge it, but one firm, energetic push will swing it wide open. It suggested that light, the most ethereal and wave-like thing we know, was actually made of particles. It challenged the very categories we use to describe reality. In the classical world, things are either particles or waves. A stone is a particle, a ripple in a pond is a wave. They are distinct, but Einstein was suggesting that light is both. It is a wave and a particle. It can act like one or the other, depending on how you look at it. This duality is one of the deepest mysteries of the quantum world. Imagine a beam of sunlight filtering through a dusty window pane. We see it spreading and filling the room, rippling like a wave, bouncing off the glass. It feels soft, continuous, embracing the space. But if we were to zoom in, past the dust motes, past the air molecules, we would find tiny quanta of energy, distinct and separate, each with its own frequency, knocking into atoms, changing the world one collision at a time. Light shimmers between these states, revealing just enough to keep us wondering, and just enough to keep us unsure. Einstein's explanation of the photoelectric effect was beautiful. It matched the experiments perfectly. It explained why the color of the light mattered more than its brightness. It showed that the energy of the universe comes in specific, granular portions. For this insight, Einstein would eventually receive the Nobel Prize. And yet, even Einstein found the path he had opened to be uncomfortable. He had revealed a world where light refused to fit into a tidy box, where the smooth continuity of nature was an illusion. We drift now in the wake of these discoveries, floating in a universe that is suddenly more textured than before. We have moved from a world of smooth streams to a world of raindrops. We have moved from a continuous ramp to a staircase of energy. The dawn of the quantum age did not arrive with a thunderclap, but with a whisper, a suggestion that the very fabric of reality is stitched together with tiny, indivisible threads. Planck and Einstein, in their quest to fix the math, had pulled back a curtain, revealing a universe that is granular, specific, and deeply mysterious. As we rest here contemplating these tiny packets of light, we can feel a shift in our understanding. We are no longer looking at a solid, unchangeable picture. We are looking at a mosaic composed of infinite tiny pieces. The light that warms your face, the glow of a lamp, the stars burning in the distant black. They are all sending their energy to you in these tiny discrete gifts. Each photon is a traveler, a messenger carrying a specific frequency, a specific story from the source to you. The universe at this fundamental level is not a clockwork machine. It is a pointillist painting, vibrant and composed of dots. It is a place where energy jumps, where light carries a punch, and where the rules of the large world begin to fray at the edges. We have found that light can be a particle. But if light, which we thought was a wave, can be a particle, then what about matter? What about the solid things, the electrons, the atoms? Could they too be hiding a secret nature? Could they too be waves in disguise? The dawn has broken over the quantum landscape. The old certainties have dissolved into a mist of photons. And as we drift deeper into this new world, we will find that the strangeness has only just begun. The particles are not just little balls. They are ghosts. They are waves. They are both and neither. The dance is about to become far more intricate and far more beautiful. We have learned that light, the very essence of illumination, is not merely a wave washing over the world, but a stream of tiny, discrete packets. We have accepted that the sunbeams warming your skin are a rain of photons, each one a microscopic traveler carrying a specific message of energy. But if light can be a particle, if the ethereal can be solid, does the reverse hold true? Can the solid things of the world, the atoms, the electrons, the very building blocks of your body, dissolve into the softness of a wave? To answer this, we must drift toward an experiment that sits at the very heart of quantum mystery. It is a simple setup, almost humble in its design, yet it contains within it a riddle so profound that it has kept physicists awake for a century. It is known as the double slit experiment. Imagine, if you will, a quiet room. It is dark, save for the soft hum of machinery. In the center of this room stands a barrier, a simple wall. Cut into this wall are two narrow vertical slits, standing side by side like tiny doorways into the unknown. Behind this barrier lies a sensitive screen, waiting to record whatever passes through the slits. And in front of the barrier, we place a source, a device capable of firing particles one by one. Let us imagine we are firing electrons, tiny, negatively charged specks of matter. In our everyday intuition, an electron is a thing. It is a microscopic marble, a tiny stone. It has weight, it has a location, and it travels in a straight line. If you were to stand before a wall with two openings and throw tennis balls at it, the result would be predictable. Some balls would bounce off the wall, others would pass through the left opening, and some would pass through the right. On the wall behind, you would expect to see two clusters of marks, one directly behind the left slit and one behind the right. Two distinct bands. This is the logic of the solid world. Things go here, or they go there. They follow a path. They do not wander. So, when scientists first performed this experiment with electrons, they expected to see those two familiar bands. They expected the electrons to behave like obedient little marbles, piling up neatly behind the openings. But the universe, in its quiet, mischievous way, had a different plan. When the experiment ran and the electrons were fired through the slits, the pattern that emerged on the back screen was not two bands. It was a series of alternating bright and dark stripes, spreading out far beyond the width of the slits. This pattern is known as an interference pattern. It is the signature of waves, not particles. Imagine dropping two pebbles into a still pond. Ripples spread out from each splash. Where the crest of one ripple meets the crest of another, the water rises higher. Where a crest meets a trough, they cancel each other out, leaving the water flat. This interplay of addition and subtraction creates a complex, beautiful pattern of peaks and valleys. This is what the electrons were doing. They were behaving like ripples in a pond, flowing through the slits, overlapping, and interfering with themselves to create a landscape of waves on the far screen. But here is where the mystery deepens, where the logic of the day dissolves into the dream logic of the night. You might think that perhaps the electrons were bumping into each other, like a crowd of people squeezing through two doors. So, the physicists decided to be very gentle. They turned down the source. They slowed the experiment down until the gun was firing only one single electron at a time. Click, One electron travels through the dark. Click. Another follows. Seconds later, there is no crowd. There is no jostling. Each electron is entirely alone in the void. Logic dictates that a single lonely electron must choose a path. It must go through the left slit or the right slit. It cannot ripple like a liquid. It cannot be in two places at once. And yet, as time passes and the single clicks accumulate on the recording screen, a ghostly image begins to form. Slowly, point by point, the same interference pattern emerges. The single electron, flying alone through the dark, somehow behaves as a wave. It implies something impossible, that the solitary particle did not choose a door. Instead, it dissolved. It became a mist of possibility. It passed through the left slit, and it passed through the right slit. It passed through both, and it passed through neither. It traveled as a ghost of itself, interfering with its own existence, exploring every possible path simultaneously, until it finally arrived at the screen and decided to become a solid point again. This is the dance of ghosts. It suggests that matter, at its core, is not solid. It is a shimmering potential. An electron is not a dot. It spreads out, testing the universe, feeling the shape of the space around it, flowing like water through the cracks of reality. It is a beautiful, fluid idea, painting a picture of a universe that is interconnected and soft. But what happens if we try to catch the ghost in the act? Human curiosity is a powerful force. We want to know. We want to see the path. And so, physicists placed a detector by the slits. They wanted to watch, to spy on the electron and see which door it actually went through. They set up a watching device, a way to measure the path without stopping the particle. They turned it on, and they fired the electrons again. And in that moment, the universe snapped shut. The moment the detector was active, the moment the path was known, the interference pattern vanished. The electrons stopped behaving like waves. They stopped exploring both paths at once. Instead, they acted like little tennis balls again. They flew in straight lines, piling up in two boring, predictable bands behind the slits. The ghost had solidified. The mist had hardened into stone. It was as if the electron knew it was being watched. When unobserved, it was free to be a wave, free to be everywhere and nowhere, dancing with itself in the dark. But the instant an observer stepped in, the instant a measurement was made, the electron felt the weight of that gaze. It was forced to choose. It could no longer be a cloud of possibilities. It had to commit to a single reality. I am here, it seemed to say, and nowhere else. This result is staggering. It tells us that the act of observation is not passive. We are not just an audience, watching a play that would happen anyway. We are part of the play. Our gaze shapes the story. When we look at the world, we are forcing it to shed its infinite possibilities and become one specific thing. The universe is shy. It reveals its wave-like magical nature only when we are not looking, only in the quiet shadows of the unmeasured. Let us drift in the implications of this for a moment. Think of the objects in your room right now. The book on the shelf, the shoes by the door. In the classical world, they are there, solid and fixed, whether you see them or not. But in the quantum dream, when you close your eyes, do they soften? Do they lose their hard edges and become gentle clouds of probability, rippling slightly in the dark? Does the universe relax when we stop asking it questions? There is a profound comfort in this idea. It suggests that at the fundamental level, reality is not rigid. It is flexible. It is waiting. The double slit experiment shows us that the world is built on a foundation of maybe. It is a tapestry woven from threads of hesitation and potential. The electron is not a prisoner of a single path. It is a traveler of all paths. It explores the left and the right, the likely and the unlikely, the straight and the winding. It embraces the entirety of the space it inhabits, and perhaps, in our own way, we are like that electron. We often feel that we must be one thing, that we must choose a single path, that we must be defined and measured and certain. But beneath the surface, beneath the labels and the expectations, we are also waves. We are clouds of potential, capable of being many things at once. We hold within us the capacity for contradiction, for being both quiet and loud, both strong and weary, both here and there. The interference pattern is a symbol of connection. It shows that even a single particle can contain multitudes. It shows that the I is never truly alone, for it interacts with itself, with its own past and its own future, creating a pattern that is richer and more complex than any straight line could ever be. The dark bands in the pattern are just as important as the bright ones. The silence is just as important as the sound. It is all part of the wave. As we leave the laboratory of the double slits, we leave behind the need for rigid answers. We accept the mystery. We accept that there are things that happen in the dark that cannot be seen in the light. We accept that the universe has a private life, a secret dance that it performs only for itself. And we are content to let it dance. We do not need to pin it down. We do not need to force it into a single shape. We can let it be a wave. We can let it flow. So, let your own mind become like that unobserved electron. Let go of the need to be in a specific place or a specific state. Let your thoughts spread out, dissolving into a soft, shimmering mist. You are not confined to a single point in the dark. You are rippling outward, gentle and weightless, floating through the slits of sleep, exploring the vast, quiet ocean of dreams that awaits you. The detector is off. No one is watching. You are free to be everything, and you are free to be nothing. You are simply drifting, a wave of peace moving through the velvet night. And perhaps, in our own way, we are like that electron. We often feel that we must be one thing, that we must choose a single path, that we must be defined and measured and certain. But beneath the surface, beneath the labels and the expectations, we are also waves. We are clouds of potential, capable of being many things at once. We hold within us the capacity for contradiction, for being both quiet and loud, both strong and weary, both here and there. The interference pattern is a symbol of connection. It shows that even a single particle can contain multitudes. It shows that the I is never truly alone, for it interacts with itself, with its own past and its own future, creating a pattern that is richer and more complex than any straight line could ever be. The dark bands in the pattern are just as important as the bright ones. The silence is just as important as the sound. It is all part of the wave. As we leave the laboratory of the double slits, we leave behind the need for rigid answers. We accept the mystery. We accept that there are things that happen in the dark that cannot be seen in the light. We accept that the universe has a private life, a secret dance that it performs only for itself. And we are content to let it dance. We do not need to pin it down. We do not need to force it into a single shape. We can let it be a wave. we can let it flow. So, let your own mind become like that unobserved electron. Let go of the need to be in a specific place or a specific state. Let your thoughts spread out, dissolving into a soft, shimmering mist. You are not confined to a single point in the dark. You are rippling outward, gentle and weightless, floating through the slits of sleep, exploring the vast, quiet ocean of dreams that awaits you. The detector is off. No one is watching. You are free to be everything, and you are free to be nothing. You are simply drifting, a wave of peace moving through the velvet night. We have watched the particles dance in the dark, behaving like ghosts that slip through two doors at once. We have seen the solid world dissolve into a shimmering interference pattern, revealing that beneath the hard surfaces of our lives. But how do we navigate such a world? If an electron is not a marble but a cloud, and if a photon is not a bullet but a ripple, how can we possibly draw a map of where they are going? To understand this, we must drift toward the quiet heartbeat of quantum mechanics, a piece of mathematics so elegant and so strange that it acts less like a formula and more like a spell. It is known as the Schrödinger equation. In the classical world, the world of apples and planets and trains, maps are very precise things. If you want to know where a planet will be next Tuesday, you use the laws of Newton. You draw a sharp, clean line through space. You place an X on the map, and the planet obeys. It arrives exactly on time, exactly where you predicted. There is no ambiguity, no hesitation. The universe is a clockwork mechanism, ticking forward with absolute certainty. But in the 1920s, as physicists peered deeper into the behavior of the very small, the clockwork began to jam. The electrons were not following the neat orbits they were supposed to. They were not behaving like miniature planets circling a miniature sun. They were doing something wilder, something softer. The universe needed a new kind of language, a language that could describe the indescribable. Enter Erwin Schrödinger. In 1926, he proposed an equation that did not describe a particle as a single point moving through the dark. Instead, it described how a wave evolves over time. Schrödinger's equation introduces us to a concept that is beautiful in its abstraction: the wave function, often denoted by the graceful Greek letter psi, $half. The wave function is a sort of mathematical whisper. It is not a hard statement of fact. It does not shout, "The electron is here." Instead, it murmurs a list of possibilities. It says, the electron might be here, or it is likely to be over there. And perhaps, just a little bit, it is also up there. The wave function is a map of mist. It describes the quantum system not as a solid object with a definite edge, but as a hazy, rippling cloud of probability. Imagine you are standing on the shore of a vast, foggy lake at twilight. You cannot see the other side. You cannot see the birds resting on the water, but you can feel the ripples lapping against your feet. You know there is movement out there, in the grey. The wave function is like the shape of that fog. It tells us where the density of the electron is thickest, where it is most likely to be found, if we were to reach out and look. But until we look, the electron is not in any one place. It is spread out. It is the fog itself. This equation allows these waves of probability to ripple and shift, flowing like water in a quiet pond. It respects the deep symmetries of nature, conserving energy and moving through time, but it cares very little for certainty. It tells us what could happen, not what will happen. And in doing so, it reveals a version of the universe that is quieter, subtler, and far more mysterious than we ever imagined. Consider the atom. Before Schrödinger, we pictured the atom as a tiny solar system, with electrons whizzing around the nucleus on fixed tracks. It was a frantic, busy image. But the wave function calms this motion down. It reveals that electrons are not orbiting in circles. They are forming standing waves. They are like the vibration of a plucked guitar string that has settled into a steady hum. They form stable, soft clouds around the nucleus, zones of presence where the electron exists as a shimmer of energy. These are not orbits, they are orbitals. They are shapes of silence and probability, blooming like invisible flowers around the center of the atom. The equation works. It has aged like fine wine, predicting the behavior of the very small with astonishing accuracy. And yet, it remains hauntingly abstract. You cannot see it with your eyes, but it is there, describing the ghostly potential of everything, from the atoms in the tea you drink to the light fading in your room. Schrödinger gave us a map, but it is a map that shifts and breathes, a guide to a territory that refuses to sit still. But the map of mist has another rule, a rule that defines the very limit of what can be known. Just as we begin to get comfortable with the idea of probability clouds, we encounter Werner Heisenberg and his famous uncertainty principle. If Schrödinger gave us the fog, Heisenberg told us that we can never truly clear it away. In the classical world, knowing things is easy. You can look at a car driving down the street and know exactly where it is and exactly how fast it is going. A radar gun gives you the speed. Your eyes give you the position. There is no contradiction. But in the quantum world, reality does not allow that kind of clarity. Heisenberg discovered a fundamental trade-off, a cosmic bargain that cannot be broken. He found that the more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. Momentum is a measure of motion, of where the particle is going and how fast. Position is a measure of where it is right now. Heisenberg tells us that these two properties are like the two ends of a seesaw. If you push one down to pin it into place, the other must rise up into the air, becoming wild and uncertain. If you try to trap an electron in a very small box to know exactly where it is, its momentum becomes a blur. It starts zipping around unpredictably, refusing to be calm. If you let it move freely so you can measure its speed, its position spreads out until it is everywhere and nowhere. This is not because our measuring tools are clumsy or crude. It is not a matter of needing better microscopes or faster cameras. The uncertainty is woven into the fabric of the universe itself. It is a feature, not a bug. Think of it like trying to hold a handful of mist. If you keep your hand open, the mist rests there, cool and present. But if you try to squeeze it, if you try to tighten your grip to hold it perfectly still, it slips through your fingers. The tighter you squeeze, the less you have. Nature does not like being pinned down. It demands a certain amount of breathing room, a certain amount of freedom. Imagine trying to find a soap bubble in a dark room. The only way to find it is to touch it. But the moment you touch it, you pop it, or you send it drifting away in a new direction. To know it is to disturb it. Heisenberg showed us that we cannot observe the universe without interacting with it, without breathing on the glasshouse of reality. But even deeper than that, even if we could touch without disturbing, the particle itself does not have a precise position and momentum at the same time. It exists as a wave, and a wave cannot be at a single point and have a single wavelength simultaneously. It must be spread out to have a rhythm. There is something strangely comforting about this principle. It tells us that knowledge has boundaries. It tells us that at the heart of everything there is a structured ambiguity, a graceful fuzziness. This fuzziness is what gives the universe its texture. It is what prevents the atom from collapsing. You might wonder, why doesn't the electron simply fall into the nucleus? The nucleus is positive, the electron is negative. They attract each other like magnets. By all classical logic, the electron should spiral inward and crash, destroying the atom in a flash of light. But the uncertainty principle saves us. If the electron were to fall into the nucleus and stay there, its position would be perfectly known. It would be right in the center. But if its position is perfectly known, its momentum would have to become infinitely uncertain, infinitely wild. It would vibrate with such intense energy that it would fling itself back out. So, the electron hovers. It finds a balance between the pull of the nucleus and the push of uncertainty. It creates a cushion of probability that keeps the atom stable, and by extension keeps all of matter stable. The chair you sit on, the floor beneath your feet, the very cells of your body, they are all held up by this refusal of the electron to be pinned down. We exist because the universe refuses to be certain. We exist because of the blur. Heisenberg's insight flips our desire for control on its head. So much of our lives is spent trying to predict, to measure, to know for sure. We want to know exactly what tomorrow will bring. We want to map out our future with sharp lines and X marks. But the quantum world invites us to make peace with not knowing. It invites us to sit quietly with the blur and appreciate the softness of what lies beneath the surface. It reminds us that the deepest truths are not always sharp-edged. They are cloudy, rippling, and perhaps that is exactly why they are so beautiful. We are not living in a rigid cage of cause and effect. We are drifting in a vast open field of potential. The map Schrödinger gave us is not a map of fences and walls. It is a map of open waters, of tides that rise and fall with the breath of the cosmos. As we drift away from the equations and the principles, let the image of the mist settle over you. Imagine that your own thoughts are losing their sharp edges. They are no longer rigid worries or hard questions. They are becoming wave functions, soft clouds of possibility, drifting through the mental sky. You do not need to know exactly where you are going tonight. You do not need to know exactly when sleep will come. You can simply exist in the uncertainty, floating in the gentle gap between being awake and being asleep. You are part of this structured ambiguity. You are a collection of atoms that are humming with uncertainty, vibrating with the energy of the wave. In that refusal to be still, there is existence. So let the fog roll in. Let the map dissolve. There is no need to navigate anymore. You are exactly where you are supposed to be, held in the gentle, fuzzy embrace of a universe that loves to dream. We have walked through the mist of the uncertainty principle, and we have accepted that the map of the quantum world is drawn in pencil, not ink. We have learned that position and momentum dance a delicate duet where knowing one requires letting go of the other. But as we drift deeper into this dream, we encounter a concept that challenges our understanding of what it means to simply be. In our daily lives, in the world of sunlight and solid ground, things tend to be in one state or another. A door is open, or it is closed. A cup is full, or it is empty. A light switch is clicked up, or it is clicked down. We find comfort in these binaries, in the clear distinction between yes and no, here and there. But in the quantum realm, this tidy division breaks down completely. We enter the shimmering domain of superposition. There is a simple image, that helps us hold this strange idea in our minds. Imagine you are holding a coin. It is a small, silver disc, cool to the touch. You flick it with your thumb, and it spins into the air. For a moment it hangs there, rotating rapidly, catching the light. In the classical world, the world of gravity and tables, we know that once the coin lands, it will be either heads or tails. And even while it is spinning, we believe that at any given microsecond, it is facing one way or the other, just blurring too fast for our eyes to see. We assume the outcome is already written, just hidden from our view. But quantum systems do not work that way. If this were a quantum coin, flipping through the vacuum of the very small, it does not secretly pick a side while it spins. Instead, it enters a state of superposition. It becomes a weighted combination of both heads and tails simultaneously. It is not undecided, and it is not switching back and forth quickly. It is genuinely, physically, in a state that is both. It is a shimmering blend of all possibilities, a single fluid object made of up and down woven together. This is the state of the unobserved universe. Before a measurement is made, the particle does not commit. It hovers in a strange and beautiful in-between. It is like a hum that contains every note of a chord, waiting to be resolved into a single tone. It is a foggy landscape where the traveler is not on the left path or the right path, but is smeared across the entire terrain, exploring every route at once. The implications of this are profound. It suggests that reality, at its most fundamental layer, is not a sequence of fixed events. It is a tapestry of possibilities, overlapping and unresolved. It is a world that allows for contradiction, where opposites can coexist in harmony. The electron spins up and it spins down. The photon goes left and it goes right. They do not choose. They simply embrace the entirety of their potential until the moment they are asked to reveal themselves. And when we do ask, when we measure, when we peak, the superposition collapses. The quantum coin hits the table. The fog snaps into a single location, like lightning illuminating one hilltop in the mist. The wave function, that mathematical cloud of maybe, vanishes, replaced by a single definite is. This transition from the many to the one is the boundary where the quantum dream touches our waking reality. But what if we tried to bring this strangeness up to our own scale? What if we took the delicate rules of the subatomic and applied them to something we could hold or pet? This question led to one of the most famous and curious metaphors in all of science. A thought experiment involving a feline, a box, and a profound question about life and death. We are speaking, of course, of Schrödinger's cat. Erwin Schrödinger, the very man who wrote the equation for the wave function, proposed this scenario in 1935. He did not intend for it to be taken literally. In fact, he devised it to highlight how absurd it would be to apply quantum rules to everyday objects. And yet the image has persisted, becoming a legend in its own right, a mascot for the mystery of the unobserved. Let us imagine a box. It is a steel chamber, perfectly sealed, perfectly quiet. Inside this box, we place a cat. It is a living, breathing creature, warm and present. Along with the cat, we place a tiny, diabolical machine. There is a small amount of a radioactive substance, so small that perhaps only a single atom might decay over the course of an hour. If the atom decays, a Geiger counter detects it, triggers a hammer, and breaks a vial of something that would cause the cat to cease to be. If the atom does not decay, the cat continues to rest peacefully. Now we close the lid. We seal the world away. We step back and we wait. According to the rigid rules of quantum mechanics, the radioactive atom is in a superposition. It has decayed, and it has not decayed at the same time. It exists in a dual state. And because the fate of the cat is tied directly to the state of the atom, the cat too must enter into superposition. In the darkness of that sealed box, before we open the lid to look, the mathematics tells us that the cat is both alive. It is not merely unknown. It is not that the cat is alive, and we just haven't checked yet. It is that the cat exists in a blurry, undefined state of being and non-being simultaneously. The timeline has split and folded over on itself. The cat is suspended in a quantum limbo, a ghost and a living soul occupying the same space. It is a strange, almost haunting image. We struggle to picture it because our minds are built for the classical world. We know cats. We know that they are either napping on the rug or they are not. We do not see them shimmering between existence and the void. Schrödinger himself found it ridiculous to think that a living animal could exist in such a blurred state. And yet the paradox forces us to confront the limits of our intuition. The box is not just a container. It is a boundary between two worlds. Inside, the rules of the quantum reign supreme. Possibility is the only reality. Outside, we stand in the classical realm, waiting for certainty. The cat is the bridge. It represents the unmeasured system, the story that has not yet chosen an ending. It represents the maybe that sits at the heart of the universe. Until observation collapses the wave function, the system contains every outcome. It holds the future where the cat walks out and purrs, and it holds the future where the box remains silent. Both futures are real, folded together in the dark. This metaphor touches on something deep within us. It speaks to the feeling of waiting, the moments in life when an outcome is undecided and we feel suspended in a state of pure potential. When we finally open the box, when we break the seal and look inside, the superposition ends. Nature is forced to choose. The blur resolves into sharpness. One history becomes real, and the other vanishes into the ether. But for that hour of waiting, for that quiet stretch of time when the lid is closed, the universe held both possibilities in its hands. It refused to destroy either one. It allowed them to coexist in a delicate, mathematical embrace. This concept of superposition is not just a philosophical puzzle. It is a resource. It is the secret power behind the emerging technology of quantum computing. In a classical computer, a bit is a switch that is either off or on, 0 or 1. But a quantum bit, or qubit, can exist in superposition. It can be 0 and 1 at the same time. This allows it to hold a vast amount of information, exploring many paths at once, solving problems by sifting through probabilities rather than testing answers one by one. It turns the maybe into a tool, harnessing the immense power of the undecided. However, superposition is incredibly fragile. It is like a soap bubble floating in a storm. The slightest touch from the outside world, a stray photon, a vibration of heat, a collision with an air molecule, can cause it to pop. This is why we do not see quantum cats in our living rooms. The environment is always watching. The air is always touching. The world is constantly measuring itself, collapsing these delicate states long before they can grow large enough for us to see. This fragility is known as decoherence, a gentle erosion of the quantum magic by the noise of the everyday. But let us return to the stillness of the box. Let us return to the beauty of the suspended state. There is a lesson here, hidden in the paradox. The universe, at its core, is not rigid. It is not a machine that grinds forward on a single track. It is a shimmering tapestry of could be. It is flexible. It is poetic. It allows for a reality where things are not fixed until they are witnessed. As you drift towards sleep tonight, you can imagine yourself in a state of gentle superposition. You are neither fully awake nor fully asleep. You are floating in the soft grey space between the two. You are holding both worlds in your mind at once. The solid world of the day you have just lived, and the fluid, dreamlike world you're about to enter. You do not need to choose just yet. You do not need to collapse the wave function of your own consciousness. You can simply be. You can be the coin spinning in the eternal twilight, catching the gleam of distant stars, never landing, just rotating in a perfect weightless rhythm. You can be the mystery inside the box, safe and sealed away from the demands of observation. In this quiet state, you are pure potential. You are infinite. The universe waits for you. It does not demand an answer. It does not demand that you be heads or tails, awake or asleep. It holds you in the soft embrace of both. And in that suspension, in that refusal to settle, there is a profound and ancient peace. Let the box remain closed for a little while longer. Let the coin spin. Let the possibilities float around you like dust motes in a sunbeam, settling slowly, one by one, as you drift deeper into the quiet dark. We have explored the solitary mystery of the particle that does not know where it is, and we have sat beside the closed box of the cat that is both living and lost. These are stories of a single system, a lonely ghost, fluctuating in the dark. But the universe is rarely a place of solitude. It is a place of relationships, of interactions, of things bumping into one another and changing forever. As we drift further into the quantum landscape, we come upon a phenomenon so strange, so deeply connected, that it challenges the very concept of distance itself. We arrive at the mystery of quantum entanglement, or what Einstein famously and skeptically called, in the world we navigate during the day, objects are distinct and separate. An apple on a table in Paris has nothing to do with an orange on a table in New York. They are independent. If someone takes a bite of the apple, the orange does not magically lose a slice. If the apple rolls off the table, the orange does not tremble. Space acts as a buffer, a vast ocean of separation that ensures things stay in their own lanes. We rely on this separation. It tells us that we are here and everything else is over there, and that nothing can affect us instantly across the miles. But in the quiet, underlying fabric of the quantum world, this rule of separation turns out to be an illusion. There exists a bond between particles that is stronger than space, deeper than time, and more intimate than any connection we can see with our eyes. This is the bond of entanglement. Let us use a gentle analogy to hold this concept in our minds. Imagine you have a pair of gloves, a left glove and a right glove. You separate them, placing each one into a box. You shuffle the boxes so you do not know which is which. Then you send one box to the other side of the world, perhaps to a quiet research station in Antarctica, while you keep the other one here with you. In the classical world, the moment you open your box and see a left-handed glove, you know instantly, without a shadow of a doubt, that the glove in Antarctica is right-handed. This is not magic, it is simple logic. The gloves were always defined. From the moment they were packed, one was left and one was right. You just didn't know it yet. The information was hidden, waiting to be revealed. But quantum entanglement is different. If these were quantum gloves, say two electrons that have interacted and become entangled, they do not leave the factory with a pre-assigned identity. They do not start as one spin up and one spin down. Instead, they leave as a pair of possibilities. They are both in a superposition of states. The electron in your box is both spin up and spin down. The electron in Antarctica is also both spin up and spin down. They are undefined. They are waiting. Here is where the magic happens. The moment you open your box, the moment you measure your electron, it is forced to decide. Let us say it decides to be spin up in that exact instant, faster than the speed of light, faster than a heartbeat, faster than any signal could ever travel. The electron in Antarctica decides to be spin down. It does not matter if they are separated by a room, a continent, or the entire width of the galaxy. The connection is instantaneous. It is as if they are not two separate objects at all, but a single object stretched across the vastness of space. This idea troubled Albert Einstein deeply. He believed in a universe of locality, where things could only influence their immediate surroundings. He believed that information could not travel faster than light, which is the cosmic speed limit. To him, the idea that a measurement here could instantly change reality over there felt like voodoo. It felt like spooky action. He argued that there must be something missing from the theory, some hidden variables or secret instructions that the particles carried with them, telling them what to do so they didn't have to communicate instantly. He wanted the universe to be like the classical gloves, predetermined and sensible. For decades, this remained a philosophical debate. Was the universe locally real, as Einstein hoped, or was it fundamentally interconnected and non-local, as quantum mechanics suggested? It wasn't until the 1960s that a physicist named John Bell devised a way to test this. He created a mathematical theorem, a way to ask the universe directly, are you carrying secret instructions, or are you making it up as you go along? When physicists finally performed the experiments, measuring entangled photons beamed across great distances, the answer came back clear and undeniable. Einstein was wrong. There were no hidden variables. The particles were not carrying secret scripts. They were genuinely undefined until the moment of measurement. The universe, it turns out, is not locally real in the way we thought. It is a vast, interconnected web where space does not break the bond between things that have once touched. This revelation changes how we perceive the void. We often think of space as emptiness, as a gap that separates us from the stars and from each other. But entanglement tells us that space is not a wall. It is a bridge. Or perhaps it is not even a bridge. Perhaps distance is just a construct, a surface-level feature that does not apply to the deep, tangled roots of reality. Imagine two particles created together in the heart of a star. They dance together, sharing their energy, their quantum state becoming a single mathematical description. Then they are flung apart. One stays in the core of the star. The other travels across the universe for billions of years, eventually landing on the retina of your eye as you gaze up at the night sky. In that moment of impact, when you see that starlight, you are interacting with that photon. You are measuring it, and in that instant, its partner, billions of light years away in the burning heart of a distant sun, adjusts its state in response to you. You are connected to that star. The thread of entanglement stretches across the eons, ignoring the vast silence of the void. The universe is not a collection of lonely islands. It is a single, breathing organism where a touch on one side is felt on the other. This connection is not a signal. You cannot use it to send a text message faster than light. You cannot use it to control the other particle, for the outcome is always random. You cannot force your electron to be up so that the other becomes down. You can only measure and accept what you find. It is a connection of shared destiny, not of control. It is a silent agreement between the particles to balance the books of the universe, to ensure that the conservation of angular momentum is honored, no matter how far apart they have drifted. Some physicists have even proposed that this entanglement is what stitches space-time itself together. They suggest that the geometry of the universe, the very fabric we walk through, emerges from the intricate web of billions upon billions of entangled particles. In this view, gravity and space are just the result of the universe holding hands with itself. Without entanglement, the universe might fragment into disconnected dust. With it, it becomes a coherent whole. As you lie there drifting in the quiet dark, think of the atoms in your own body. They were forged in the hearts of ancient stars. They have interacted with countless other particles over billions of years. Who is to say what subtle threads of entanglement still linger? Who is to say what connections you hold to the deep cosmos? You are not small, and you are not isolated. You are a knot in the great quantum web. The separation between you and the world is soft, porous, and ultimately an illusion. You are entangled with the air you breathe, with the gravity that holds you, and with the light that fades from the room. And just as the entangled particles harmonize their dance across the universe without ever exchanging a word, you do not need to do anything to be connected. You do not need to send a signal or make an effort. The connection is already there. It is woven into your very substance. Let the feeling of isolation dissolve. Let the distance between you and your dreams, between you and the stars, collapse into a single point of presence. There is no over there. There is only here. The universe is holding you, and in some strange quantum way, you are holding it back. The threads across the void are strong, and they are humming with the quiet promise that nothing is ever truly alone. You can rest in this interconnectedness. You can float on the web of the world, knowing that every part of you is balanced by the whole. The spooky action is not scary. It is a comfort. It is the assurance that we are part of a system that remembers us, a system that coordinates its movements in a vast, silent symphony of spin and light. Sleep now, held by these invisible hands, secure in the knowledge that the void is not empty, but full of invisible threads connecting everything to everything else. We have entangled ourselves with the distant stars, and we have rested in the uncertainty of the spinning coin. But now, we must turn our attention to something that seems, at first glance, to be the most reliable thing in the world: a wall. In our everyday experience, walls are the ultimate definition of no. If you walk into a wall, you stop. If you throw a tennis ball at a brick barrier, it bounces back. The laws of classical physics are very strict about this. They tell us that if an object does not have enough energy to climb over a hill or break through a barrier, it must stay on this side. It is trapped. The boundary is absolute. But in the quantum world, the word absolute loses its meaning. In this shimmering realm, the walls are not as solid as they appear. They are porous. They are probabilistic. They are suggestions rather than commands. We arrive now at one of the most magical phenomena in all of physics, a process known as quantum tunneling. Imagine a particle, perhaps an electron, approaching a barrier In the classical view, this particle is a tiny, hard marble. If the barrier is a high-energy hill and the marble is rolling slowly, it will simply roll partway up, lose its momentum, and roll back down. It cannot pass. But remember, our electron is not a marble. It is a wave. It is a cloud of probability that spreads out through space. When the electron wave meets the barrier, it does not just bounce off abruptly. Instead, the wave pushes into the wall. It penetrates the barrier, its intensity fading exponentially as it goes deeper. Think of it like a sound being muffled by a thick curtain. The sound is loud on one side, and it gets quieter and quieter as it travels through the fabric. But if the curtain is not too thick, and if the sound is loud enough, a faint whisper of it will emerge on the other side. This is exactly what happens to the electron. The tail of its wave function stretches through the forbidden zone. It tapers off, becoming a mere ghost of a probability, but it does not vanish completely. And because the wave function tells us where the particle can be found, this means there is a small but non-zero chance that the electron will simply appear on the other side. It does not drill a hole. It does not break the wall. It does not squeeze through a crack. It simply fades out of existence on one side and fades into existence on the other. It tunnels through the impossible. It cheats the classical rules of energy conservation for a brief, fleeting moment, borrowing just enough uncertainty to make the leap. This phenomenon might sound like a rare curiosity, a parlor trick performed by shy particles in a dark lab. But in truth, it is the reason you are alive. It is the reason the sun rises in the morning and warms your face. It is the reason the universe is filled with light. Let us drift for a moment to the heart of our sun. It is a place of immense pressure and heat, a cosmic furnace where hydrogen nuclei are crushed together. These nuclei are protons positively charged, and like magnets with the same polarity, they hate to be close to one another. They repel each other with a fierce electric force. This repulsion is a barrier, a wall of energy that prevents them from touching, from fusing, from becoming something new. According to classical physics, the temperature of the sun, even at 15 million degrees, is not hot enough to push these protons through that barrier. They should bounce off each other eternally. The sun should be dark. It should be a cold, dead ball of gas. But the sun shines. And it shines because of quantum tunneling. In the chaotic dance of the solar core, protons get close. They push against the electric wall. And every so often, thanks to their wave-like nature, a proton does not bounce back. Instead, it tunnels through the repulsion. Its wave function reaches across the gap, and it finds itself suddenly in the embrace of another proton. They fuse. They release a tiny burst of energy. This event is incredibly rare for any single proton. It might happen only once in billions of years. But the sun is vast. It holds an unimaginable number of particles. And so these rare ghostly crossings happen countless times every second, creating a steady, radiant roar of fusion that powers the solar system. The light that feeds the plants, the warmth that drives the winds, the energy that flows through your body. It is all a gift from particles that walked through walls. We see this magic here on Earth as well. Deep inside the atoms of heavy elements, particles are trapped behind the strong walls of the nucleus. But sometimes they grow restless. An alpha particle made of 2 protons and 2 neutrons will tunnel its way out, escaping its prison to fly free. This is radioactive decay. It is the sound of matter unlocking itself, the slow ticking of the atomic clock. And we have learned to harness this ghostly ability. Scientists have built devices called scanning tunneling microscopes. They bring a tiny, sharp metal tip incredibly close to a surface without ever touching it. The gap between the tip and the surface is a barrier, a wall of empty space. But electrons, eager to explore, tunnel across that gap. They flow like a quiet current from the surface to the tip. By measuring this current, we can feel the shape of atoms. We can map the bumps and valleys of the molecular landscape. We can see the building blocks of matter, not by touching them, but by catching the electrons that have slipped through the void. It is a beautiful thought, isn't it? That the barriers we perceive as solid are actually permeable. That separation is not absolute. In the quantum world, there is always a chance, however small, to overcome an obstacle that seems insurmountable. The particle does not force its way through. It surrenders to its own wave nature. It becomes soft. It extends itself beyond the limit of where it is supposed to be, and in doing so, it finds a way to the other side. Think of the walls in your own life, the limits of your energy, the boundaries of your knowledge, the distance between you and a dream. We often view these as hard stops, but perhaps, like the electron, we are more wave-like than we know. Perhaps our influence, our thoughts, and our potential extend further than we realize, tunneling through the barriers of time and circumstance. The lesson of tunneling is one of quiet persistence and subtle possibility. It teaches us that impossible is just a classical word for highly unlikely. It teaches us that if you wait long enough, if you allow yourself to be fluid enough, the way forward will open up. The sun does not shine because it is powerful enough to break the rules. It shines because it is patient enough to let the rules bend. It relies on the softness of the universe. It relies on the mist. As you lie in the safety of your room, look at the walls around you. In the dim light, they look solid. They define the space. But you now know the secret. You know that deep down in the buzzing silence of the atoms, those walls are mostly empty space and probability fields. They are shimmering curtains of force, and the particles within them are constantly testing the boundaries, constantly whispering to the other side. You are safe, enclosed in a sanctuary of rest. But you are not trapped. Your mind is free to tunnel through the ceiling, past the roof, and up into the cool night air. You are free to drift to the moon, to the sun, to the very edge of the cosmos. There are no walls for a dreamer. There are only new spaces waiting to be entered. Let the concept of barriers dissolve. Let the tension in your muscles melt away, just as the resistance of the barrier melts for the tunneling electron. You are flowing. You are passing through the heavy gates of wakefulness, leaving the solid world behind. You are slipping quietly, effortlessly, into the vast open landscape of sleep. The way is open. The transition is smooth. You have already crossed the threshold. We have traveled through walls, and we have felt the invisible threads that bind the galaxy together. Now we must turn our gaze to the spaces in between. When we look up at the night sky, we see the bright points of stars, the glowing trails of comets, and the swirling arms of distant galaxies. But mostly, what we see is black. We see the void. In our everyday language, we call this nothing. We think of nothingness as a lack. It is the empty room after the furniture has been moved out. It is the blank page before the ink touches it. It is the silence that falls when the music stops. We imagine the vacuum of space as a cold, dead stage, a passive backdrop where the real actors, the stars and planets, perform their plays. We assume that if we were to take a box of space and remove every single atom, every molecule of gas, every photon of light, and shield it from all gravity, we would be left with a perfect still emptiness. Of the quantum world, in its infinite richness, tells us that our intuition is wrong. It whispers a secret that changes everything. There is no such thing as empty. The void is not a lack of things. It is a fullness of potential. The silence is not quiet. It is humming. This is not the vacuum of a cleaning machine, nor is it the simple emptiness of a jar. It is a restless, jittering stage. It is a sea of energy that heaves and breathes, even in the deepest, darkest corners of the universe. Even when we have removed every particle that can be removed. It is far from blank. It seethes with invisible activity, a foam of possibilities bubbling just beneath the surface of reality. To understand this, we must return to our old friend, the uncertainty principle. We learned that we cannot know a particle's position and momentum at the same time. But Heisenberg's rule also applies to another pair of qualities: energy and time. It tells us that for very short periods of time, the amount of energy in a system can fluctuate wildly. Nature allows a tiny loan of energy to be taken out of nothingness, as long as it is paid back quickly. The shorter the time, the larger the energy loan can be. This means that empty space is constantly borrowing energy from itself. In these fleeting moments of borrowed time, the vacuum gives birth. Out of the nothingness, pairs of particles spontaneously pop into existence. They are called virtual particles. They appear in pairs, a particle and its antiparticle, dancing into reality for a fraction of a nanosecond, only to collide and annihilate each other, returning their energy back to the void. They are called virtual, not because they are imaginary, but because they are ephemeral. They are ghosts of the quantum world, appearing and disappearing faster than we can directly detect them. They are like the foam on the crest of a wave, flickering in and out of sight. Imagine the space around you right now, the air in your room, the space between your eyes and the screen. It is not empty. It is teeming with these temporary visitors. Electrons and positrons, quarks and antiquarks, photons of all frequencies, they are all bubbling up and vanishing in a ceaseless, silent firework display that creates the fabric of space itself. You might think that if these particles vanish so quickly, they do not matter, that they are just a mathematical curiosity, a dream of the equations, that the quantum vacuum has weight. It has force. And in one of the most beautiful experiments in physics, we can actually feel it pushing back. This is known as the Casimir effect. Imagine taking two metal plates, perfectly flat, perfectly smooth mirrors. You place them in a vacuum, facing each other, and you bring them incredibly close together, so close that they are almost touching, separated by a gap of only a few nanometers. According to classical physics, there is nothing between the plates and nothing outside the plates. It is all just empty space. The plates should hang there, still and lifeless. But quantum mechanics asks us to look at the waves. The virtual particles of the vacuum appear as waves of all sizes, some long, rolling waves, and some short, choppy ripples. Outside the plates in the vast open space, waves of all sizes can exist. The ocean of the vacuum is wild and unrestricted, but between the plates, the space is cramped. Only the small waves fit. The long waves are excluded, just as a large ocean swell cannot fit into a small harbor. This creates an imbalance. Outside, there is a crashing sea of all possible waves, pushing against the plates. Inside there is a calm, restricted pool with fewer waves. The pressure from the full vacuum outside is greater than the pressure from the quiet vacuum inside. And so, the plates move. They are pushed together by the sheer weight of nothingness. The invisible activity of the vacuum exerts a physical force, a gentle squeeze that we can measure in the laboratory. It is as if the universe is hugging the plates, pressing them close with its invisible arms. This is not theory, it is fact. We have seen the plates move. We have felt the substance of the void. This phenomenon reminds us that nothing is a powerful thing. The vacuum is the baseline of the universe, the canvas upon which all else is painted. But it is not a canvas of cloth. It is a canvas of water, rippling and active. Every atom in your body exists within this sea. The electrons in your cells are not just orbiting in emptiness. They are swimming through this quantum foam. In fact, the interactions with these virtual particles subtly shift the energy levels of atoms. If the vacuum were truly empty, hydrogen atoms would behave slightly differently. But they don't. They behave exactly as if they are being buffeted by the gentle, invisible winds of the virtual sea. The vacuum connects everything. It is the fundamental field of all. Every other field, electromagnetic, gravitational, nuclear, is just a ripple on top of this restless background. It is the hum beneath the silence. It is the glow behind the darkness. Cosmologists even believe that the energy of this vacuum might be responsible for the fate of the entire universe. There is a mysterious force pushing the universe apart, making it expand faster and faster every day. We call it dark energy. While we do not fully understand it yet, many suspect it is the energy of the vacuum itself, the cost of having space. As the universe grows, it creates more vacuum, and that new vacuum comes with its own intrinsic energy, pushing outward, stretching the cosmos like a growing breath. But let us bring this back to the room where you rest. Let us bring it back to the feeling of stillness. It can be easy to feel small or isolated when we think of the vast, cold emptiness of space. We often fear the void. We fear the silence, thinking it means we are alone. But the quantum vacuum offers a different perspective. It tells us that stillness is not an absence of life. It is the presence of latent potential. The space around you is alive with invisible activity. It is holding you. There is no place in the universe where you are truly alone. For even in the deepest isolation, the vacuum is there, dancing its eternal dance. Think of the silence in your mind as you drift towards sleep. We often try to fill our minds with noise, with thoughts, with plans, with worries, because we are afraid of the blank space. We are afraid that if we stop thinking, we will cease to be. But the quantum lesson is that the blank space is rich. The pause between thoughts is not empty. It is a reservoir of peace. Just as the vacuum gives birth to particles, your quiet mind gives birth to dreams. Just as the empty space holds the energy to push galaxies apart, your rest holds the energy to renew your spirit. The nothing is where the everything comes from. So, do not be afraid of the dark. Do not be afraid of the quiet. Imagine yourself floating in that quantum sea. You are weightless, suspended in a medium that is thick with possibility. The air around you is soft and supportive. The pressure of the universe is not crushing you. It is embracing you, like the plates in the Casimir experiment, gently holding you together. The vacuum hums. Can you hear it? It is a sound lower than hearing, a vibration slower than time. It is the sound of the universe breathing. It is the sound of existence emerging from the void, moment by moment. You are made of this. You are a ripple in the fullness. You are a temporary, beautiful fluctuation in the eternal field. And as you let go of your waking self, as you let your own particles soften and blur, you are simply returning to the rhythm of the sea. You are sinking into the restless, jittering stage that underlies all things, finding your place in the great, full emptiness. Rest now in the fullness. Let the vacuum carry you. There is so much life in the silence. There is so much presence in the dark. You are safe in the arms of the nothing that is everything. We have lingered in the fullness of the vacuum, and we have felt the gentle pressure of nothingness. Now, as we drift deeper into the heart of the quantum dream, we arrive at a crossroads. It is not a crossroads of asphalt and signs, but a fork in the very river of time. We must confront the most personal and profound mystery of them all, the moment of choice. We have spoken of the wave function, that shimmering mathematical cloud that holds all possibilities at once. We know that before we look, the electron is here and there. The cat is alive and dead. The coin is heads and tails. But we also know, from every moment of our waking lives, that we never see the world this way. When we open our eyes, we see a single truth. The coin lands on heads. The cat is sleeping on the rug. The electron dots the screen in one precise spot. Somewhere between the silence of the wave and the certainty of our experience, a decision is made. The cloud condenses. The fog snaps into a single raindrop. Physicists call this wave function collapse. It is the moment the universe seemingly makes up its mind. But how? And why? Does the universe prefer one story over another? Or is there a deeper, stranger secret hiding behind the curtain of reality? For a long time, the standard answer came from a misty city in Denmark. This is the Copenhagen interpretation, championed by Niels Bohr. In this view, the wave function is not a physical thing, but a book of betting odds. It tells us what we might see. And when we look, when we measure, we force the universe to choose. The act of observation is the author that writes the end of the sentence. The other possibilities, they vanish. They are deleted from existence as if they never were. It is a pragmatic view, clean and efficient. It says, there is only one world, and you are creating it moment by moment with your gaze. But there is a loneliness to this idea. It suggests that every time a choice is made, infinite other futures are destroyed. The road not taken is burned away. In 1957, a young physicist named Hugh Everett III looked at the mathematics and proposed something radical, something so vast and generous that it sounds like a myth. He asked, what if the wave function never collapses? What if the universe never chooses? What if, instead of snapping into one reality, the universe simply makes room for them all? Welcome to the many worlds interpretation. Imagine you are standing on the shore of a calm ocean. You toss a pebble into the water. In the Copenhagen view, the pebble sinks, and that is the end of the story. But in Everett's view, the ocean is the universe, and it is limitless. When you toss the pebble, the universe splits. In one branch of reality, the pebble sinks. In another, it skips across the surface. In yet another, a bird catches it mid-air. Everett suggested that every time a quantum interaction has multiple possible outcomes, all of them happen. The universe does not prune the tree of possibilities. It grows new branches. This means that when you flip a quantum coin, it does not land on heads or tails. It lands on heads and tails, but in separate worlds. In this branch, the one you are conscious of right now, you see heads. You smile and say, "It's heads." But in a parallel branch, just as real, just as physical, another version of you sees tails. That version of you is just as convinced that they are the real you. They have the same memories, the same feelings, the same name. They just saw a different side of the coin. These worlds are not ghost stories. They are not hypothetical scenarios in a philosopher's mind. According to this theory, they are real, physical universes vibrating alongside our own. They are parallel shores, separated not by distance, but by the direction of the wave function. Once the split happens, the branches drift apart. They decohere, meaning they can no longer speak to one another. You cannot wave to your other self. You cannot peek across the divide. The other path is silent to you, but it is loud with life for the version of you walking it. It is a dizzying thought. It suggests that reality is not a single line, but a vast, branching coral reef, growing exponentially with every passing nanosecond. Every electron that goes left instead of right creates a new timeline. Every photon that hits a leaf instead of a stone spins off a new universe. The cosmos is not a single melody. It is an infinite symphony, playing every possible variation of the song at once. This might feel overwhelming. A universe of infinite copies, a library of never-ending stories, but there is a deep, quiet comfort to be found here if we let ourselves drift into the philosophy of the multiverse. Think of the choices you have made in your life, the turns you took and the turns you didn't. We often carry the heavy weight of what if. What if I had taken that job? What if I had said the words I held back? What if I had turned left instead of right? In the singular view of Copenhagen, those unchosen paths are dead. They are lost potential. But in the many worlds, nothing is ever lost. The what if is simply a description of another place. In the shimmering lattice of the multiverse, there is a branch where you did take that job. There is a branch where you did speak your heart. There is a world where the mistake was never made, and a world where the lucky break happened yesterday. Every possibility is inked into existence somewhere. The universe is infinitely generous. It does not force you to sacrifice one future for another. It gives you all of them. You, the consciousness listening to this now, are simply riding one specific current in a limitless river. This perspective softens the edges of regret. It tells us that we do not need to worry about missing out, because in the grand scheme of the quantum tree, we miss nothing. We are living the total experience of existence, spread across the branches of a vast and shimmering library. And what of the randomness? We learned that we cannot predict the outcome of a measurement, that God plays dice. In many worlds, the dice are an illusion. The outcome is not random. It is inevitable. Everything happens. The randomness is just a question of which branch you find yourself on. It shifts the question from what will happen to which world am I in? Imagine a tree growing in slow motion. The trunk is the past, solid and shared. The branches are the future, splitting and reaching toward the light. You are a leaf on one of those tips. You can feel the wind of your own unique moment. But you are connected, deep down in the wood, to all the other leaves. You are part of the same great organism. There is also a humbleness in this view. It reminds us that our perspective is limited. We see only a sliver of the whole. We see the heads of the coin and think that is the only reality. But the tails is just as true. The universe is far larger, far richer, and far more complex than our single set of eyes can perceive. And what keeps these worlds apart? Why don't they crash into each other? It is the process of decoherence, the same gentle fading we spoke of earlier. As systems interact with the environment, they become entangled with the world around them. This entanglement locks them into their specific branch. It creates a layer of ice over the quantum water, preventing the different histories from mixing. It ensures that your reality feels stable, consistent, and singular, even while the storm of possibilities rages silently next door. So, as you rest here, let your mind wander through the branches. You do not need to understand the math of the Hilbert space or the mechanics of orthogonality. You only need to feel the width of it. Feel the spaciousness of a reality that allows for everything. If you are worried about a decision you have to make tomorrow, remember the many worlds. Remember that in some sense, you will make both choices. You will travel both roads. You are free from the pressure of having to get it perfectly right, because the universe is exploring every angle on your behalf. You are a multi-dimensional traveler. You are an explorer of the infinite. And right here, right now, in this specific quiet branch of the cosmos, you are safe. You are resting. This version of you, the one listening to my voice, has chosen stillness. And that is a beautiful choice to make. Let the other versions of you run their races and fight their battles in the other worlds. Tonight, your task is simple. Your task is to sleep. Your task is to let go of the branching possibilities and settle into the soft, warm certainty of this moment, this breath, this bed. The wave function of your day is collapsing into the night. The noise of the multiverse is fading into a single, peaceful silence, drifting, branching, sleeping. We have wandered through many strange landscapes tonight. We have seen particles that act like ghosts, and we have stood on the branching shores of parallel worlds. But now, I invite you to dissolve the world even further. Imagine pulling back the curtain on everything you see. The stars, the oceans, your chair, your hand, even the light falling gently on your pillow. We are going to look beneath the atoms, beneath the protons, to find the very fabric of existence. In the classical view, we tend to think of the universe as a collection of things. We imagine it like a vast Lego set, built from tiny, solid blocks. We think of an electron as a little marble, and a photon as a little bullet. But if you listen closely to the whispers of modern physics, you will hear a different story. You will hear the melody of quantum field theory. In this profound view, the universe is not made of stuff at all. It is made of fields. It is built from vibrations, waves, and invisible ripples spreading through mediums that fill all of space. The vacuum is not empty. It is a layered mattress of these fields, piled on top of one another, humming in silence. Let us drift into this concept gently. Imagine a calm ocean, extending infinitely in all directions. The water is the field. Now, imagine a wave rising up from that water. The wave is not a separate object. You cannot take the wave out of the ocean and put it in a box. The wave is a behavior of the ocean. It is a localized ripple, a momentary excitation of the water. This is what a particle is. An electron is not a tiny stone. It is a ripple in the electron field. This field exists everywhere, in your room, in the space between galaxies, inside your heart. When you see an electron, you are seeing a place where the field has been plucked, where it has gathered enough energy to pop up and say, "I am here." When the electron moves, it is not a marble rolling across a floor. It is a ripple transferring its energy through the field, like a swell moving across the sea. And this is true for everything. For every particle we know, there is a corresponding field. There is a photon field for light. There are quark fields for the nucleus. There is a gluon field for the glue that holds atoms together. The universe is an infinite orchestra of overlapping notes, and reality is simply the music that emerges from their interference and harmony. Let us meet the musicians in this quiet symphony. Physicists call this collection the Standard Model. It is the ingredient list of the cosmos, a surprisingly compact recipe that describes almost everything we have ever touched or seen. First, we have the quarks. These are the heavy, stable notes that make up the core of matter. They come in 6 flavors, a word physicists use with a whimsical smile. There are the up and down quarks, the common workers that build protons and neutrons. And then there are the exotic ones: charm, strange, top and bottom. These heavier quarks are like rare chords that are struck only in high-energy moments, flashing into existence in cosmic rays or particle colliders before fading back into the silence. Then we have the leptons. You know the most famous one, the electron. It is the buzzing, energetic soloist that dances around the atom, carrying electricity and weaving the chemistry of life. But it has cousins too. The muon and the tau are heavier, fleeting versions of the electron. And then there are the neutrinos. These are the introverts of the universe. They are incredibly light, shy, and elusive. Billions of them are passing through your body right now, streaming from the sun, but they interact with almost nothing. They drift through the solid earth as if it was smoke. Or they are the silent observers of the symphony. That a symphony needs more than just notes. It needs connection. It needs a way for the instruments to talk to one another. This is the role of the bosons, the force carriers. When 2 electrons repel each other, they are not touching. They are exchanging a message. They are tossing a photon back and forth between them. The photon is the carrier of the electromagnetic force. It is the quantum handshake that tells the electrons to move apart. Every beam of light you have ever seen is a stream of these messengers. Then there are the gluons. These are the carriers of the strong nuclear force. They are the sticky, energetic particles that bind quarks together inside the proton. They are like a very excitable group of toddlers, constantly exchanging energy, ensuring that the nucleus remains solid and stable. Without them, matter would simply drift apart, like dust. And finally, we must speak of the Higgs boson and the all-encompassing Higgs field. For a long time, this was the missing piece of the puzzle, the ghost in the machine. Confirmed only recently, the Higgs field is a cosmic molasses that permeates all of space. As particles move through this field, they feel a drag, a resistance. This resistance is what we call mass. Imagine walking through water. It is harder to move than walking through the air. The water gives you weight. The Higgs field does this for particles. The more a particle interacts with the Higgs field, the heavier it is. A photon slips through the Higgs field like a needle, feeling no resistance. and so it remains massless and travels at the speed of light. An electron feels a little drag, so it has a little mass. A top quark feels a lot of drag, so it is heavy. Without this field, none of this would have any weight. The universe would be a blur of massless radiation, unable to form atoms, unable to form stars, unable to form you. All of these fields interact with one another in a dance of breathtaking precision. This interaction is described by quantum electrodynamics, or QED. It is the theory of light and matter, the crown jewel of physics. It explains how an electron emits a photon, how light bounces off a mirror, and how atoms hold their shape. Richard Feynman, a physicist with a bongo drum and a playful mind, gave us a way to visualize this dance. He drew simple diagrams, lines and squiggles that represent the complex interactions of fields. A straight line for an electron, a wiggly line for a photon. These diagrams are not just drawings. They are maps of probability. They tell us that particles take every possible path. When light travels from a lamp to your eye, it does not just take the straightest line. In the quantum view, it tries every path. It bounces off the ceiling, it loops around the moon, it dances to the edge of the galaxy and back. But all those wild paths cancel each other out, leaving only the path of least time, the path we see. The universe calculates the infinite sum of all possibilities to deliver the single reality of a sunbeam. QED is so precise that its predictions match experiments to within the width of a human hair compared to the width of North America. It is poetry written in calculus. It describes a world where the interaction of light and matter is a performance choreographed by rules so subtle we barely notice them. Yet they are responsible for every color, every reflection. So, here we are, nestled in this world of fields. It changes how we see ourselves. You are not a solid object separated from the rest of the world by your skin. You are a collection of ripples in the same fields that make up the stars. You don't end at your skin. The electron field that vibrates in the atoms of your fingertips is continuous with the electron field that vibrates in the air you breathe. The heat you radiate is a disturbance in the electromagnetic field that stretches out to the ends of the universe. You are a delicate pattern in the cosmic fabric. There is no sharp edge where you stop, and the universe begins. There is only a softening. You are a localized song in a boundless atmosphere. You are a knot in the golden thread. This perspective dissolves the loneliness of individuality. We are all woven from the same loom. The fields that make up the ancient galaxies are the same fields that make up your dreams. We are interwoven in a dance too fast, too subtle, and too beautiful to ever fully catch. As you lie there, feel the hum of these fields. Feel the gravity holding you. A conversation between your mass and the curvature of space. Feel the warmth of the blankets. A transfer of photon energy. Feel the stability of your body. The gluons holding you together. The Higgs field giving you substance. You are a symphony. You are a vibration. And tonight, the music is slowing down. The ripples are becoming gentle. The high-energy notes of the day are fading, leaving only the deep, resonant hum of rest. You are returning to the baseline. You are floating in the great, quiet ocean of the quantum field, waiting for the next movement to begin. But for now, there is only the pause. There is only the silence between the notes. And it is perfect. We have explored the cold, quiet vacuum, and we have listened to the symphony of fields that hums beneath the structure of the universe. In our journey so far, we have mostly visited the realm of the inanimate, the lonely electron, the distant star, the abstract wave function. We tend to think of quantum physics as something fragile, something that belongs in the frozen silence of a high-tech laboratory, isolated from the noise and warmth of the real world. We assume that the messy, wet, chaotic environment of living things is too loud for the delicate whispers of the quantum ghost to be heard. Biology is warm, quantum states are frozen. Biology is solid, quantum states are fluid. Surely, life operates on the sensible, classical rules of chemistry and mechanics. But as we drift into the final chapter of our exploration, we find that nature, in its infinite ingenuity, has a surprise for us. Life, it seems, has been listening to the quantum whisper for billions of years. It has learned to harness the strange tools of the subatomic world, to navigate, to eat, and perhaps even to smell. Consider the robin, a small, unassuming bird with a breast of red rust, migrating thousands of miles across the globe with uncanny precision. It flies through the dark, through storms, over oceans where no landmarks exist. How does it find its way? For a long time, we suspected birds had a built-in compass, but the mechanism was a mystery. Now the evidence points to something radical: quantum entanglement. Deep inside the robin's eye, within a specific protein called cryptochrome, there is a dance of electrons. When light hits this molecule, it excites a pair of electrons, causing them to become entangled. They are linked, spinning in a shared quantum state. This delicate pair becomes incredibly sensitive to the weak magnetic field of the Earth. As the bird turns its head, the magnetic field tugs gently on the entangled electrons, altering a chemical reaction in the eye. This means the bird is not just seeing the world of trees and worms, it is seeing the magnetic field lines of the planet painted across its vision like a heads-up display. It is navigating by the spooky action of quantum mechanics. A living creature, warm and breathing, is holding a fragile quantum state in its eye, using the connection between particles to find its way home. And it is not just the birds. The plants that line our streets and fill our forests are also quantum masters. Think of a leaf bathing in the sunlight. Photosynthesis is the process of turning that light into chemical energy. It sounds simple, but it is a race against time. When a photon hits a chlorophyll molecule, its energy must be transferred to a reaction center to be stored. If it wanders around randomly, bumping from molecule to molecule like a ball in a pinball machine, it would lose energy and die out. But plants are incredibly efficient, almost perfectly so. How? Measurements suggest that the energy does not bounce randomly. Instead, it enters a state of quantum coherence. It spreads out like a wave. It behaves like the electron in the double-slit experiment, exploring multiple paths simultaneously. Imagine dropping a marble into a maze. Instead of rolling down one corridor and hitting a dead end, the marble turns into water. It floods the entire maze at once, feeling every possible route, and then instantly pools at the exit. That is how a plant eats sunlight. It uses the quantum shortcut, taking all paths at once to find the most efficient way to life. The green of the forest is the color of quantum efficiency. Even your own body might be part of this strangeness. There is a theory about our sense of smell. Usually, we think of smell as a lock and key mechanism. A molecule has a shape, and it fits into a receptor in your nose. But there are puzzles this theory cannot solve. Some molecules with different shapes smell the same, and some with the same shape smell different. The alternative is the vibrational theory. It suggests that when a scent molecule enters your nose, your receptors are not just feeling its shape, they are listening to its vibration. An electron in your receptor tunnels across the scent molecule, and it can only make the jump if the molecule is vibrating at the right frequency. If this is true, then every time you smell a rose, or coffee, or rain on asphalt, you are experiencing quantum tunneling. Your nose is a quantum device, sniffing the vibrations of the atomic world. Life, it seems, is not separate from the quantum dream. It is woven into it. We are biological machines, yes, but we are built on a foundation of quantum magic. But the strangeness does not end with biology. It extends to the very flow of time itself. We are used to time moving in one direction, forward, past causes, future. I drop the glass, and then it breaks. But in the quantum world, the arrow of time is not so straight. We return to the delayed choice experiment and the quantum eraser. These are experiments that seem to suggest that a choice made now can affect what happened then. Remember the double slit experiment? If we measure the particle, it acts like a particle. If we don't, it acts like a wave. But what if we wait? What if we let the particle pass through the slits, let it travel through the dark, and only after it has finished its journey do we decide whether to look at the data that tells us which path it took? The results are mind-bending. If we decide to look at the which path information, even after the particle has supposedly landed, the particle behaves as if it had been a particle all along. But if we decide to erase that information to destroy the record of which path it took, the particle behaves as if it had been a wave all along. It is as if the particle is waiting for us to make up our minds in the future, before it decides what it did in the past. It implies that history, at the quantum level, is not fixed. It is a cloud of possibility that only settles into a story when the information is finalized. Time is not a rigid track. It is a web of correlations. The future and the past are shaking hands in the dark. This brings us to the final, quiet mystery: randomness. Einstein famously said, "God does not play dice with the universe." He wanted a world of strict order, where every effect has a precise cause. But quantum mechanics tells us that at the bottom of everything, there is pure, irreducible chance. When an electron hits a screen, its location is random. When an atom decays, the moment is random. This randomness is not chaos. It is not messy. It is structured ambiguity. It is a kind of freedom. If the universe were perfectly deterministic, like a clock, then everything that happens, every word you speak, every thought you think, would have been predetermined at the moment of the Big Bang. There would be no room for novelty, no room for surprise. But the quantum dice roll gives the universe flexibility. It allows for mutation in evolution. It allows for the new to emerge from the old. It suggests that the future is not written in stone, but drawn from a deck of infinite possibilities. Randomness is the engine of variety. It is the reason no two snowflakes are alike. It is the reason you are unique. You are an improbable collection of atoms, brought together by billions of years of quantum chances, held in place by fields, powered by tunneling sunbeams, navigating by entangled lights. So, as we come to the end of our content loop, we are living in a universe where walls are permeable, where empty space is full, where particles can be in two places at once, and where time folds back on itself. This is not a scary world. It is a soft world. It is a world that refuses to be rigid. It is a world that prefers the maybe to the must. And you are a part of it. You are not an observer standing outside the glass. You are the glass. You are the light. You are the wave. The quantum world is not out there. It is in here. It is in the breath you take. It is in the firing of the neurons in your brain, tiny electrical sparks, jumping gaps, possibly tunneling, possibly entangled. Your consciousness itself might be the ultimate quantum phenomenon, a wave of awareness surfing on the ocean of fields. The time has come to stop trying to understand. The intellect has done its work. Now, it is time for the intuition to take over. It is time to let the facts dissolve into feelings. The paradoxes are not problems to be solved. They are lullabies to be heard. Let the randomness comfort you. It means you are free. Let the entanglement hold you. It means you are connected. Let the superposition soothe you. It means you have infinite potential. We have reached the end of the knowing. Now we begin the feeling. The script of the universe is not a textbook. It is a dream. And you are the dreamer. Thank you for drifting through the quantum dream with me tonight. We have traveled a very long way, journeying from the familiar solidity of the world we see down into the shimmering, misty depths of the world that is. We have wandered through the dawn of the particle and the wave, watched the ghostly dance of electrons, and floated upon the vast invisible ocean of fields that connects every heartbeat to the furthest star. And now we have arrived at the quietest shore of all. We have reached the point where the seeking ends and the resting begins. Throughout this journey, we have encountered mysteries that defy our logic, paradoxes that challenge our sense of order, and truths that seem to dissolve the moment we try to hold them too tightly. We have seen that the universe is not a rigid machine of gears and levers grinding forward with indifferent precision. Instead, we have found a universe that is soft. We have found a reality that is hesitant, fluid, and deeply responsive to presence. We have found a cosmos that waits for us, a world that is built on a foundation of maybe rather than must. It is easy in our waking lives to feel the pressure of certainty. We often feel that we must know exactly where we are going, exactly who we are, and exactly what tomorrow will bring. We build walls of expectation and trace sharp lines of definition around our lives. But the quantum world offers us a profound permission to let all of that go. It whispers to us that certainty is an illusion, a temporary mask worn by a reality that is fundamentally open. You do not need to be solid right now. You do not need to be defined. Just as the electron spreads out into a cloud of probability when it is not being watched, you too can allow the edges of yourself to soften. You can release the need to be in a specific state. You can release the need to hold a specific shape. In the safety of this night, in the privacy of your rest, you are free to become a wave. You are free to ripple out into the darkness, weightless and unburdened, exploring the infinite possibilities of the dream world. You are not separate from the strange wonders we have explored. You are not a stranger looking in at the quantum realm.
You are the quantum realm.
The atoms that form your hands, the oxygen that flows into your lungs, the electrical signals that drift through your mind, they are all dancing the same dance. You are woven from the same threads of entanglement that stitch the universe together. You are a symphony of vibration, a localized song in the vast silence of existence. And because you are part of this fabric, you are held by it. The universe is not empty space, it is a fullness that supports you. The vacuum is not a void, it is a cradle of energy. You are resting in a cosmos that is alive with connection, a web of relationships that stretches across time and space to ensure that you are never truly alone. If these calm, curious explorations help you unwind, I invite you to like or subscribe. It helps other sleepy souls find their way here too. And now, let all of those concepts drift away. Let the images of spinning coins and branching worlds dissolve into the velvet dark. Let the names of the physicists and the shapes of the equations fade like mist in the morning sun. Your mind has done enough work. Your curiosity has been satisfied. The intellect can lay down its tools. The laboratory of the mind is closing for the night. The lights are dimming, one by one, turning off the machines, quieting the detectors, covering the chalkboards. The questions have all been asked, and the answers have all been turned into lullabies. There is nothing left to solve. There is nothing left to measure. The universe will continue its complex, beautiful dance without your supervision. The particles will continue to tunnel, the fields will continue to hum, and the stars will continue to burn, all held in the gentle embrace of natural law. You do not need to understand it to be part of it. You only need to be. Turn your attention back to the simple, rhythmic rise and fall of your chest. Feel the gravity of the earth, that grand curvature of space-time, pulling you gently down into your mattress. It is a constant, steady hug, anchoring you in the now. Imagine that you are a wave function that is slowly spreading out. You are expanding beyond the room, beyond the house, drifting into the cool, quiet air of the night. You are becoming smooth. You are becoming peaceful. You are entering the state of superposition between the waking world and the sleeping world, floating in the soft gray space where anything is possible. Let the silence of the vacuum wrap around you. It is a heavy, warm silence, a blanket of potential. It quiets the noise of the day. It smooths out the worries of the past. It erases the anxieties of the future. There is only this moment. There is only this breath. You are safe. You are connected. You are infinite. The arrow of time is slowing down for you. The randomness of the world is settling into a pattern of perfect rest. Become the wave. Close your eyes. Let the darkness hold you. Drift into the mystery.